What we have seen so far is how we can make a move using a train policy, meaning a trained neural network, and using Monte Carlo tree search. So when you rehearse the last two slides, you should be able to understand, if you have the model already trained, how you can use it to automatically make the next move, given any state in the game, any board position. What we will look into now is how we actually arrive at a neural network that includes or implements a trained policy. And if we have that, we have AlphaGo 0. We have everything we need. So how do we train the policy and value network? It's actually not just a policy, it also gives you the value of the next state. So it's a policy and value network combined in one. And again, it could be any machine learning approach, but neural networks are specifically good for that at the moment. But if you're not an expert in deep learning yet, you can just think of an SVM or something like that. Take something in, gives an output. How do we train that thing? We will see 3 successive steps now, and this is the first one. The first one is how do we create the training experience, the data that we need in order to learn something. And we will create that by self-play, by playing against ourselves. We will somehow bootstrap our model from scratch without any human intervention. For those who already know something about reinforcement learning, this is also called the policy evaluation step in a general framework called policy iteration, sorry. So the AlphaZero approach falls generally in the reinforcement learning area of so-called policy iteration or generalized policy iteration, which has 2 steps. And the first one is policy evaluation. But this is for those who already know a little bit. How do we create the training experience? How do we come up with something? First thing is, we create our machine learning model, the policy, by randomly initializing. It's a neural network, so we randomly initialize all the weights like we usually do it. We start with a random parameterized network. And of course, we can also already use that. It takes in the usual input, it puts out something in the correct chain. It will just output something random, but we can still use it. So what do we do with it? We make a loop for, in the paper, it's 25,000 iterations. We play 25,000 games. Could also be 50,000, 10,000, 25,000 work for. How is it done? They use Monte Carlo tree search, see last slide. And the currently best, in the beginning, this is our randomly initialized model for the moves of both players, black and white. This is why we can do self-play. We can do a move for black, then we use the same model, do a move for white, and so on. Use it for both. For each move in each of these 25,000 games, what do we do? And the move we do, like we saw on the last slide, we record the current game state. How is the game state represented? Previously I told you it could just be, for example, an image of the board. And it's actually something like that. It's a stack of 19 by 19 matrices, where you can have one number for every possible intersection of the grid. You have 1 for all the positions of the black stones. You have 1 for all the positions of the white stones. Then you have 7 more for the 7 previous positions of the black stones, 7 more for the 7 previous positions of the white stones, and another one that is all black or all white to indicate which turns it is, whose turn it is. So overall, we have a stack of 19 by 19 arrays. You could imagine that as a small image with black and white pixels, and 17 feature maps, like 17 channels. If you know something about computer vision and neural networks, usually this is your image, and the depth here is your color channel, R, G, and B. Here we have 17 color channels. And this you can, of course, put in a standard convolutional neural network. How this looks like, we will see later. So we record for every move in every one of these games the state like that. That is the representation of the current state, not the last 7 states. we do from the current state a search using Monte Carlo tree search. Output of that search is the output vector, the probability for every possible action. We record these probabilities as they come out of the Monte Carlo tree search. That is, we have a probability distribution per action that is proportional to how often a specific path was taken, how often a specific action was taken in the first branching of the tree. This gives us, if we normalize it, the probability distribution for the first action we can take from that state. Is that clear? We have the current state, we do the tree search to the end of the game, and then we see how often did we take every possible action we could take. We just take the ends out of the branches from the tree search. And if we normalize these numbers, we have the probability distribution over all the actions. How probable is it? How often did we went down that path? So we record the search probabilities, and when we've played that to the very end, we record who won. Black or white. Or maybe it's on the other way around, but we record who won. That is everything we record for every move in every game. This is how we get data to learn from. When we have done 25,000 games, we trigger a retraining of the neural network that until now was just randomly initialized, so was just random guessing. So from these first 25,000 games, we do not expect anything. But because we use a tree search, still actions that are more plausible should somehow more often lead to wins, just because we do a random sample. So we've done 25,000 games, we trigger retraining. You can imagine that runs on a different machine. So we trigger retraining on a different machine, and we just continue with this. Just continue creating data, playing with ourselves, with the same network. What does happen in retraining? This is the next step. We retrain the neural network. For those who know reinforcement learning, in the policy iteration framework, this is called policy improvement. The second step in policy iteration. What do we do here? First, we do something that has been called experience replay in the reinforcement learning literature. It was developed in that famous paper, also from DeepMind, where they solved several Atari games with a specific algorithm. They found out you cannot just work on your current data, you always have to bring in data from far more previous games so that your network does not do something that is known as catastrophic forgetting. It means if you always train on the newest stuff, it will forget what it has learned or seen before. So you do something like experience replay, you sample from all your previous iterations, from all the previous data you created, you sample some game states. So you do this. You create a mini batch of 2048 positions, states, from the last 500,000 self-play games. So now you have a mini batch of data. What do? You retrain your neural network. And this is now just standard supervised learning, like you do it with any machine learning algorithm. You have a specific input, that's a game state, and you have an output that should be the probability of the actions and the value, and you know what should be the result from how you created the data. How does it look like specifically? Your input are the specific game states that you sample here. The output are the move probabilities, P, this P vector, probability of each possible action, this vector, and I just dropped the vector notation here, like we usually do in machine learning, plus the value of the resulting state. No, sorry, of the current state. The probability of winning from that state. This should be the output. What is the ground truth? How do we do supervised learning? The labels are, or the ground truth, the search probabilities that came from the Monte Carlo tree search. Remember here? The normalized wizard counts from the tree search. These are our training ground truth labels. We want to resemble this in our neural network. We want to build our intuition, our neural network, to match what our tactics model does in thousands of simulation runs. We want to capture that knowledge in the neural network. So this is why our labels are for the move probabilities are the search probabilities as they come out from MCTS. And so this is the ground truth for the P, and the ground truth for the value of winning is just who actually won. If I actually won in that state, then Z will be 1, then the value should be 1. If I lost, I get a -1 here, and I would have a 0 here. So maybe I get a 0 here as well. Needs to be normalized, of course. What is the loss? Standard loss function, how you would use it in supervised learning. That could probably be a very interesting task to solve. What would be the loss function if you know this is input, output, labels? For this part, it's classification, and you need these probabilities. You have a softmax that you somehow need to realize, so it's probably a standard classification loss, so it's cross entropy, usually.
But they don't are numbers because there are search probabilities.
Pardon?
It is P.
Yes.
Pi. Pi. Despite
Yeah.
the search probabilities. These are the labels that we are training for.
Yes.
And these are numbers.
Yes.
And why use cross entropy? Not.
I have a distribution here and I have a distribution here. This is what you usually have in multi-class classification. Usually in multi-class classification, this is all 0 except of 1. This has a 1.
So
But still you can compare these two distributions with cross entropy.
okay.
It's exactly the same as you have in multi-class classification. For this part, and for the later part, it's more regression. You want to make these numbers match each other. So you can use, for example, these data. So you have a component for the classification part, a component for the regression part, and you have a component for regularization, and that's it. That is pretty straightforward. It might be harder to imagine it when you don't see it, but if you read it, this is super straightforward. You have a classification part, you have the regression part, you have the regularization part. That's it. You add 3 up. Maybe you have some scaling parameters between, but that's a loss function. You could now go forth and implement that. When you've done that, you start the training, you retrain the neural network, and if you retrained it, you want to know how good is it now. That leads you to the third part. After creating of data, retraining the network, now you want to evaluate it. And you do evaluate it not after every training, because this is just one batch. You do it after 1,000 batches. So after 1,000 epochs, so to say. After 1,000, so on the very first computer, you let the self-play stuff run. And after 25,000 games, you re-triggered neural network training. This runs for 1,000 mini batches, and then it triggers on the third machine, you can imagine, the evaluation. And here, on the second machine, just the retraining continues with all the data we currently have. So one machine is continually playing and creating data, the other machine is continually training, and the third machine is continually evaluating. How does evaluation work? So evaluating the last network that was built. You play, and here it's 400, but of course it's hyperparameter as well, 400 games between the currently best model that we have seen that achieved the highest scores in this game, against the latest, the last model we just created. We let both play against each other, so we know we use one for the black stones, one for the white stones, and we see who wins. How do we do it? 400 games. Each move is done by Monte Carlo tree search and using the respective network. And we do the playing deterministically. Meaning, we will always choose the action with the highest probability. Of course, we could put in some exploration here. Remember, very much in the beginning we talked about exploration and exploitation. During training, we are always doing this. We are not always taking the highest probable action, but we are sampling according to the distribution, which puts some randomness on it. That allows for exploration, for doing some moves that are not very likely, but to learn something new. Here in evaluation, we play deterministically. We always take the maximum probability action. We let both networks play against each other, and if the new network wins more than 55% of the matches, it's the new best network, which will be used again in step 1 for creating more training experience. And as you learned from the video of Professor Silva in the beginning, they did that for 40 days. And probably not just on 1, 2, 3 machines, but a little more hardware or a little more capable hardware than your standard gaming workstation. And then you arrive at an agent that can beat the world champion in one of the most famous strategy games of the world. And that's all that is to AlphaZero. You have a tree search, you have a neural network, and you have that supervised training from data created by Selfplay. Quickly have a look at all the components. I didn't create that myself. It's from a very interesting blog post in the Applied Data Science blog that basically says these are the 4 components of the Selfplay. Why is Selfplay important for the thing? If you have a neural network that starts from random, so it does not know anything about the game, and it plays against your colleague who knows something about Go, it will lose all the time. And it will never see any positive reward because it loses all the time. It will never improve. But if it plays against itself, it always has an opponent that is on par with it. At the beginning, it's completely random, but the opponent is also random. So sometimes it loses, sometimes it wins. If it improves, or after it improves, it will also be used for the other turns. So it will have an opponent that is on par with it. So this way, the Selfplay is really crucial here for it to work. Otherwise, it wouldn't learn as quickly, or it wouldn't learn at all. Selfplay ensures that it always has somebody it can learn from on the same level, not much better, not much worse. Second thing, how the network is retrained. Supervised learning, using as a supervision goal, not some perfect gold standard, but what the Monte Carlo tree search gave us outputs. We just try to mimic what our tactic module currently gives us. This is not perfect, but obviously enough to estimate good moves. Last thing, how do we evaluate the network? We just play against each other. We say the one that wins more often is a better one. Last ingredient, how we actually implement, encode the game state. Very standard thing if you come from computer vision. You just put in everything as a matrix, as an image. And if you have more features, you put them in as different channels. And then we have the 2 components algorithmically, the tree search, how you traverse a tree and how you add things to the tree, and we have the neural network. Actually, you can see the complete architecture of the network here, but this is not important for this course. Let's take this as given. If it would be in the deep learning course, we would probably look more deeply into how does this correspond to that representation, but that doesn't matter. So this is a complete overview of what are the ingredients for that thing to work. We're almost at the end. For those that will go on looking into reinforcement learning, I want to highlight very quickly just a few concepts that you will encounter when you see more of reinforcement learning that have been used here. The overall framework, like the mathematical framework under which you can understand many of the concepts in reinforcement learning, is called Markov decision processes. If you know something about a Markov decision process, this is what is underlying every reinforcement learning agent. It's basically a decision process, a process where you sequentially have to take decisions, what to do next, where every decision is just dependent on the last decision and not on the thing more back into the past. That means everything you need to know about the past needs to be encoded in the last observation. This is why the past has been encoded into the state here, because it is modeled like a Markov decision process, where your future is independent of the past given the present. we actually do not rely here just on the observation. We have used some modeling to arrive at a specific representation of a state that includes the past. We are solving a planning problem, not just a learning problem. We are solving a problem where we plan ahead using explicit planning algorithms like the tree search. We use a model of the environment. This is a simulation of the game. We are not playing with hardware in the real world and a human opponent. We are playing with a simulation, so it's model-based reinforcement learning. And we are learning a value function, a function that can map from state to the value of the state, the probability of the game. We use something called dynamic programming, policy iteration, I already mentioned it, and we're using Monte Carlo methods, using randomness. If you hear a course on reinforcement learning, you will encounter all these words before you encounter the first application of it. So if you start learning about reinforcement learning, you will hear these words, and this way, with this slide, you can somehow connect it. This is why it's here. I will not say much more about it, because it will be too abstract without going into details. There are a couple of things mentioned in these 2 lines that are from really top-notch research in reinforcement learning that have been applied here that are very important for it to work. Yeah, take it as a reference when you start learning more about reinforcement learning. It's not so important for the content of this course. Let's quickly talk about the implications of that work, and this is the last slide on it. In the popular press, people made a huge buzz about the advent of this method of AlphaZero. Why? Because the last resort of human mind, like the greatest strategy game on earth, unable to play by computers, and now it's solved by computers, and the computer's better. Now we will lose everything to the machines, right? This is what you usually read in public newspapers. And it doesn't matter if it's Blick or NZZ, they all write the same on it. Why is that one way to look at it, but in its entirety completely false? The thing learns to play without any human intervention, just by playing with itself. This is very interesting. A very interesting concept, and it does it really well. It is a very simple and principled approach. If you look again over the slides, you will realize you can, with just information on the slides, rewrite the program, let it run, it will probably work, given enough time and hardware. So it's really a simple thing. It doesn't have lots of bells and whistles and specific things that are Go specific. It's just a nice and elegant approach. It's really cool. And the performance, I mean, is really fascinating. And we've seen the same thing also for Capture the Flag with the Quake engine, with Dota 2 that is combining strategy and 3D. RL has made a lot of progress, and this is actually something people can be proud of, and that wasn't expected before. But the stuff is still handcrafted. The AlphaZero approach works for AlphaZero because it specifically focuses on specific aspects of what makes Go Go. It's a fully observable game. It has no randomness in it. It has exactly 2 outcomes, win and loss. It doesn't have draws. It took them a while to also make it work for chess, where the only change basically is that you have draw games. It doesn't generalize very well to something else. You cannot use this and build a self-driving car with it. So this is not an agent that will learn by itself to become better than humans in anything else but Go. If you want to go deeper into that, I would advise you to read another article by Andrei Karpathy. I think we had one of him 2 weeks ago. He had a very interesting fact check on what is cool in AlphaZero, AlphaGo still then, and why it's not the super hype that the public press makes out of it. Why you can still be very proud of it as somebody who knows the technology behind it and has played it, but why it will not make you fear that the machines take over. So you have to keep these 2 things in tension. It's super cool, but it's not the end of the world as we know it, or the beginning of a new age, or whatever. Finally, That's a very interesting thing. I took quite some time in the beginning to convince you that reinforcement learning is completely different than supervised learning. That's a different approach, it's much more general, this is why it takes much longer and it's much more fragile to train. And now we saw an approach that works like charm on a specific problem, and what is it? Supervised learning. That is somehow the tension in which the field of reinforcement learning currently is. We have so much know-how of supervised learning techniques that sometimes, when you know your hammer really well and you just have a hammer, every problem looks like a nail. Reinforcement learning is much more than supervised learning, it's much more general, all this stuff is true, but currently, because we have such breakthroughs in supervised learning, many people cast their reinforcement learning problems as a supervised learning problem, add some tricks, like that experience replay that we saw, and it works, and then we're happy. But it's not yet solved. There's a lot of things to do in reinforcement learning at the moment. Absolutely final last word on that. If you want to read a really great paper and get inspired on how to write scientific literature yourself, for example, for your master thesis, read the original article in Untitled. It's 5 pages, so it's not very long. It's a very good example of how to write, how to make good figures, how to make very clear what you mean, how to make it very concise, and how to still make it comprehensible. So if you want to read one good article, not yet as preparation for the exam, but just for reading a good article, read this one. Thank you very much for bearing with me and staying in the course. If you want to try out something in reinforcement learning, start with this. This example should work within a couple of hours. It's about a simpler game and a simpler reinforcement learning approach. Everything is on Moodle. You can try it out. There are code templates. You have probably to write 1 or 2 pages of code yourself, and then it should work. That's it for the lecture. Thank you very much.